The name of the course is Dislocations and Strengthening Mechanisms of Solids. So we divide materials into several parts. Let me just write. The main categories are firstly metals, right? How can we subdivide metals? How can we categorize metals? Ismail, do you have any idea?
FCC, BCC maybe.
Based on crystal structure?
Mm-hmm.
Maybe we can categorize them firstly based on chemical composition, like ferrous materials, right? And non-ferrous materials. Ferrous means Fe based. Non-Fe based, non-ferrous. Fe base is very simple, right? Like steel or cast iron. You can go ahead and check the iron carbon phase diagram. And non-ferrous are the basic elements, right? Aluminum, copper, titanium, tungsten, tin. What else? What else we have? We have several, right? You can add niobium, zirconium, etc., etc. The second category is polymers. How can we subdivide polymers? What are the main categories of polymers? Any idea? Ramazan? Ramazan Ünal, do you have any idea?
Maybe it can be thermoplastics for them.
Perfect. Thermoplastics, for example. Very good idea. Thermoplastics. What else we have? Other than thermoplastics, we can have thermosets, right? Or elastomers. Ismail, can you give an example to thermoplastics? Anything that comes into your mind?
I don't know.
Thermoplastic. Maybe PVC, right? PVC or nylon. Or acrylic. These are all thermoplastics. Thermosets, for example, epoxies. Elastomers, like, I don't know, rubbers, let's say. Or silicones. Other group is ceramics. let's say ceramics and let's say ceramics, okay. Any example to ceramic group?
Can be glasses.
Great, glasses. Right, oxides, nitrides. Perfect, glass. Graphite. Or very, very pure elements like diamonds. And if we combine any two categories and we get better mechanical properties, we call it composites. Oops. Any example like could be any metal matrix or ceramic matrix, for example. Or reinforced plastics. All right, this is the general picture of the materials. And in this course, we will mainly focus on metals. And the name is dislocations and strengthening mechanisms. What do you guys understand when I say dislocation? Any idea what is dislocation? Actually, you guys know it from 218, ME 218.
Hocam, can I say?
Please go ahead.
Collective movement of the atom migration.
Perfect. And they are the carriers of plastic deformations, right? Plastic deformation. And when I say strengthening mechanisms, so we will investigate the plastic deformation. Plastic deformation, okay. Strengthening mechanisms. What is the goal of strengthening mechanisms? They basically enhance the strength of a material. And how do we measure the strength of a material? How can we measure the properties of materials?
Tensile test.
We do basic tests, right? We have some tests. We do testing and measure some properties. You said tensile test. Or if you pull the material, elongate the material, decrease the cross-sectional area. So this is the area instantaneous. This is area 0. This is initial length. Let's say this is L final. After tensile or compressive tests, basically we get force versus displacement curve. Then we can convert this information to stress, which is nothing but just force divided by area versus displacement, or let's say strain, which is just elongation delta L, which is L final minus L initial divided by initial length. The unit is unitless, let's say millimeter divided by millimeter. And what's the unit of stress? Let's say the unit of force is Newton, and the unit of area, let's say millimeter square. And we have megapascal. Basically, the unit is Pascal. For brittle materials, we have only elastic region. But for ductile materials, we also have some plastic region. Then the stress that separates the elastic region from plastic region is yield stress. Slope of elastic region is modulus of elasticity. We have failure strain, which is ductility. We have the maximum stress, which is sigma ultimate tensile stress, and the area under this curve is toughness of a material. Therefore, after tensile or compressive test, we measure the strength of a material via quantifying the yield stress, ultimate tensile stress, or fracture stress. Ductility of a material, fracture strain. We can measure the stiffness of a material. What is the unit of stiffness? Modulus of elasticity. It's again Pascal, right? Mostly for metals, the elastic modulus is in between 190 gigapascal and 210 gigapascal. And we can measure toughness. When I say strengthening mechanism, that means the components that consist of this particular specific stress. For example, this value. What are the mechanisms that dictates, that compose that stress? And when I say dislocation, that means they are the carriers of plastic deformation. That means without any dislocation, we don't have any plastic deformation. Okay. So we will mainly investigate this plastic region and the different strengthening mechanisms, and we'll try to answer the question of how can we enhance the strength of a material. For example, your application requires the stress levels of this much or this much. You want to make your material more stronger to withstand the desired stress level. That is why you need some more strengthening mechanism you need to activate. And if you guys don't know what are the strengthening mechanisms, you cannot activate them. Okay, speaking of testing and properties, what are other tests do we have?
Hardness hocam.
Hardness, you said. We just apply compressive force to the material and we measure the resistance of the material to this compressive strength, and we measure basically the hardness of a material. We have different kind of hardness tests, and the property that we get from hardness is basically hardness itself. What else?
Can we say torsion test?
Torsion, good. Instead of pulling or pushing the material, you just apply some torque to your material. You just twist the material, and while twisting your material, see this. We create some shear stress, right? We can calculate it through the amount of torque we are applying to system, C over G. Then we can measure the shear stress instead of normal stress. What else? What else? What other tests do we have?
Impact test.
Impact, perfect. Impact test. Basically, for impact test, we have a hammer that has a potential energy, perfect rock creep test, like high temperature creep test. So for impact test, we have a impact hammer that has a potential energy. We just release the hammer, draw it. We have a hammer which has a potential energy around maybe 300 joule. We place the material here, which has a notch, and the purpose of creating notch is just create a stress concentration, right? This is stress concentration point. Then we hit the sample and we observe the amount of energy that the sample stores, and we measure the impact energy versus, we just monitor the impact energy versus temperature curve. Let me quickly draw impact energy versus temperature. For BCC material, they are pretty ductile at high temperatures. So this is BCC. But FCC, so here we have some temperature, critical temperature, which is ductile to brittle transition temperature. And we have some transition from brittle to ductile region. Basically, the material, the BCC material like tungsten, right, or BCC iron, they show ductile behavior at these temperatures, but before this critical ductile to brittle transition, they show brittle behavior. Actually, that is why the giant ship Titanic failed. It's an engineering disaster. They just test the materials, BCC bolts at high temperatures, and they think the materials are ductile. But once the Titanic hit the iceberg, they just fail very flat, very random, very rapid, which is very unexpected and catastrophic. How about for FCC materials? Do we have any ductile to brittle transition temperature? For FCC? For FCC, the behavior is more like this. We have something like this, then, of course, its temperature, it will decrease, but we don't have a specific ductile to brittle transition temperature. And for high strength materials, of course, BCCs are also very strong, very strong. Also, Martensite phase is very strong. But if we specify high strength materials, we also have such a graph. So what is the reason do you think we have, and also maybe HZP is here? Sometimes, for example, if you measure zinc for an HZP material, you can also observe something like this. This is also HZP. But if you measure, for example, titanium, you can get something like this. But what is the main reason we have a critical ductile to brittle transition temperature for BCC material, but not for FCC or HCP materials? That would be the reason. Any idea? Let's think about it. Let's think about it. So let's think about their deformation mechanisms. How do they deform and how do they create this plasticity? What are their deformation mechanisms? Let's start with FCC. Ismail, do you know the deformation mechanism of face-centered cubic materials?
Hocam, actually, I forgot those.
All right. Then before going to deformation mechanisms, let me basically draw a multi-scale material modeling or multi-scale approach of material science. So let's say this is the scale of time and this is the scale of length. So we are living in a macro world, right? So this could be a second to hours, say to hours. And so it's not decades, like second, hours, hour words, basically. And millimeter or let's say meter. So this is macro world. And we see the bulk material. For example, it's macro world. I just see this metal key, for example. This is just the second time scale. And this is for me like some centimeter length scale. we see the bulk material. Once we go to microvert, microsecond, erase this and draw it. Oops, sorry. Let me go back. All right. Microsecond and micrometer. What do we see? If you put your material under the microscope, what do you guys observe at microscale, both
Grains.
length and time?
Grains.
Grains, right? We have different grains. We have different grains of materials. So the material is not that perfect. So if you go a bit scale down, maybe you can observe the dislocations. Or let's not write the dislocation to microvert. Maybe once we go to nanosecond and nanometer here, what do we observe if you put your material under transition electron microscope, TEM? What can we see at nanoscale?
Atoms, hocam.
Atoms, right? We have a bunch of atoms bonded with each other, but sometimes it's not that perfect. We have some missing atom, we can have some extra bond, we can have missing bonds, we can have an vacancy. Let's say this is vacancy. So it is more chaotic. It is not perfect. This word is chaotic. So let's go down. Let's go to picosecond, femtosecond, picometer, femtometer. Then what do we observe?
Quarks maybe hocam.
Maybe quarks, like the subatomic particles. But like, think about the one scale down of this cluster. Maybe we can see, because quarks are not picometer, they are very, very small, right?
Atomic bonds hocam maybe.
Very good, very good. Maybe we can observe the vibrations. We can observe that each atom, say this is the harmonic oscillator, and the atom is going back and forth, right? They're just vibrating at the bottom of harmonic oscillator. Then we have some oscillations. Here we have some mesoscale. Mesoscale, we do some crystal plasticity, material modeling. At microscale, so each scale we do different modelings. For example, at atomic scale, we do basic first principle calculations in modeling, like ab initio. With either WASP or quantum espresso. In order to measure the these scale properties. Then the main goal is just set the bridge between different scales and go up to macro world or continuum scale. Maybe at continuum scale, we can have better predictions. So at nanoscale, the model that we conduct is mostly molecular dynamics. We do some semi-empirical potentials and we do molecular dynamic simulations. At microscale, we do some rate fields. By the way, molecular dynamics, the platform is mostly lamps. And of course, Monte Carlo or kinetic Monte Carlo. I'll explain the distance later, the difference later. Maybe at mesoscale, we can run some discrete dislocation dynamics, etc. But whatever, let me not mention about the models. Let me just go back and continue from the vibrations. Okay, the motivation is set the bridge between different scales. So while starting my PhD, the community told me we are going to this direction. You have to focus on this direction. But now I see that instead going to this direction, the world has gone to this direction. We focus more on atomic events. And with the aid of computational power, we can calculate lots of properties using atomic scale codes. For example, using ab initio, using atomic models, we can calculate the specific heat, for example. So the world has gone in this way. Speaking of specific heat, actually that was the first attempt. Started in 1900s. I don't know, I think maybe 1899. There are two scientists called Dulong and Petit. They assume that specific heat is nothing, but since, let me call this is specific heat of Dulong and Petit's law. This is 3, which is the degree of freedom, Avogadro's number, times the Boltzmann factor. Boltzmann is the one that created the statistical mechanics. And this formula yields us, if you plot the specific heat, right, which is, what's the unit of specific heat? Any idea what was the unit? Surely you guys know, right? Joule divided by mole Kelvin and temperature. This model yields, we have a constant specific heat at every temperature. So the specific heat doesn't depend on any temperature dependence. There is no temperature dependence. Then scientists made some experiments and they observed at high temperature, that is really the case. Specific heat is more or less these values very close to each other. But after certain temperature or before certain temperature, we have lower specific heat values. Let me draw like this. We have lower specific heat values. All right, let's draw like this, sorry. Then we have saturation. Then basically Boltzmann couldn't find the answer of this question and he died. Then Einstein came into the picture and he proposed to quantize the energy. He proposed to quantize the energy. And the story begins around, I think, 15. Max Planck proposed the black body radiation, and he showed that using classical physics, he couldn't capture the electromagnetic emission, but once he quantized the energy, he get the real emission curves. Then Einstein also proposed, okay, we have atoms and with springs, they are connected with each other. And for each atom, they just vibrate at the bottom of harmonic oscillator and they create some vibration. Once he input the ground energy and quantum theory, once he quantized the energy, he got such a formula. He relates let's say Einstein is proportional with 1 over t squared. To be exact, it was like 3 and kb. Could be mistaken maybe, but as far as I remember, this is like TE divided by t squared, and we have some exponential term, exponential TE divided by t, and we also have exponential TE divided by t minus 1 square. This should be the formula. I'm not 100% sure, but I'm sure it's proportional with 1 over t squared. Then once we plot the Einstein equation, we capture the low temperature values. So this is, sorry. Einstein model is something like this. This is Einstein model, and this one is the green one is Dulong and Petit. So far, so good. But Einstein also had some mismatch in between experimental values and numerical values. Then there is another scientist came into the picture, and he said that, wait a second, the atoms are not individual. Once they vibrate, they also affect the neighbor atom. So once one atom vibrates back and forth, it also affects the vibration of the neighbor atom. And they create some phonon. That is what we call it, phonon wave. And Debye proposed the phonon wave. Main difference, okay, Debye except the energy is quantized, and he also applied the ground state energy with quantum mechanics. And he also mentioned that they are not individual atoms, but they do affect one another. Then they create some phonon scattering, some phonon wave. So the third model is Debye. And let's write CV Debye. And Debye said that CVD is nothing but, I don't remember the whole formulation, but he said that it is proportional with, instead of T square, now it is proportional with 1 over T cube. So this is Einstein temperature. The Debye temperature is 9 kb. Debye temperature divided by some T cube. So it is, this should be just Debye should be here. Debye to T cube, and he has some integral from 0 to T Debye divided by T. And here we have some exponential term. And here we have y4, I think EY, we will get the integral with respect to dy, and I think should be e to the y minus 1. This should be the formula of Debye, but again, I'm not 100% sure. Once he plots this formula, he got real good estimation, the best estimation, Debye. And he actually find the way how does the FCC material deform. Basically, FCC material deform via phonon scattering. That is why at low stresses, we suddenly activate the dislocations for FCC material. Give me an example of FCC material. Let's think about FCC materials. Erşan Mert, do you have any FCC material that comes into your mind?
Aluminum.
Perfect. Aluminium is FCC. Aluminium, copper. What else?
Gold.
Gold is FCC. Perfect. Aluminium, copper, gold. And if you think about them, once you apply any any load, you can activate the dislocations. And what did we say? Dislocations are carriers of plastic deformation. And plastic deformation is nothing but shape change, right? Permanent shape change. Once you unload your material, you have some elastic recovery, but this is the permanent shape change. You cannot go back to the original position. Think about aluminum, think about paper clips. You can easily bend them. You can give a permanent shape change. It's very, very low stresses. That is why we have. The reason is the deformation mechanism is just phonon scattering. You apply a load, you activate all the dislocations, okay? Then you have plastic deformation, pure FCC that I'm talking about. It's not the, for example, it's not bronze. It is not like tin versus any other element. We don't have any solid solution strengthening pure aluminum. I'm talking about, for example, pure gold. Once you take gold, and if you try to bend the gold, you can easily bend the gold, right? So the deformation, they are mostly deformed via phonon scattering and with edge dislocations. But BCCs are different. They are very strong, but they are very brittle. And FCC, they are weak. They are weak, but they are ductile. That is, the difference is the deformation mechanism of FCC is mostly phonon scattering, but for BCC, we need some thermal activation. We need some, for example, we have a slip plane. Let's say this is 110 slip plane. And you have a dislocation here. And you have an energy barrier. And your energy barrier again, here, something like this. Okay, and your dislocation is here at this energy scale, For BCC materials, in order for this dislocation to jump other energy scale, you need to overcome this energy barrier. This is the energy barrier, delta E. And to overcome this energy barrier, you need to load your material until very high stresses. That is why you don't have dislocation activities till maybe 400 megapascal, 500 megapascal. That is why they are very strong. Once you plot their stress and strain, you will see that BCCs are very strong, but they do not possess a significant ductility. You cannot activate the dislocations easily. You need to overcome this energy barrier. But FCC materials, you can activate the dislocation very easily. Very little elastic deformation, then plastic deformation, and boom, failure. They are not that strong. That is why we need to increase the strength of FCC materials without sacrificing from ductility. And we need to increase the strength level of ductility level of BCC material. So this is BCC. The dashed line is idealized BCC. And yellow is FCC. And this is ideal FCC. Here we have some thermal activation. If you look at the Gibbs free energy calculations, if the Gibbs free energy is less than 0, of course, the event is spontaneous. But if you go ahead and check the energy barrier of this dislocation, you will see that it depends on temperature. But if you check the velocity of edge dislocation, the phonon scattering, the edge dislocation, you will see that the velocity of dislocation is nothing. It's athermal. It doesn't depend on temperature. It is tau B over B. Here, tau is shear stress. B is Berger's vector. B is direct coefficient, like the resistance. And if you plot the speed of dislocation and apply shear stress, you will see speed and apply shear stress, meter per second, Pascal. You will activate the dislocation right away. Even at 1 megapascal, you have a dislocation activity for edge dislocation. So they are linearly correlated with each other. But once you reach the speed of sound in a material, the velocity is nothing but the speed of sound in the material. For example, I don't know, if you use iron, you need to check the speed of sound in iron. That is the maximum velocity that your dislocation can reach. If you're using aluminum, just find the speed. They are different. Speed of sound in aluminum is different than the speed of sound in iron, and that is the maximum velocity you can reach with your edge dislocations. So far, is there any question? Roa, did you get everything? Roa?
Yes, Hocam, I'm here.
Yeah, is there any question?
No, all is clear, Hocam.
Perfect, perfect. Resul, do you want to ask anything?
No, hocam, all clear. Thank you.
Then let's take 5-10 minutes break and continue to second class.